Okay, let's get started, y'all. So, reminder, we have a exam coming up, paper version next Tuesday. So this coming Tuesday, March 27th, and then the coding portion of the exam Wednesday, March 28th. And on Tuesday, I went over the particular details of the exam, so I'm not going to repeat them. If you weren't here on Tuesday or you want to brush up on what it's about, go and look at the videotape lecture for Tuesday. The details are all there. There will be an after-class activity today, and what I think I'm going to do is, in Code Assessor, have you do one of the problems from Dr. Planck's exams, because it's a little tougher than the problems I would ask you on the exam, but I think it's good practice with sets and maps, and if you can do that one, then you should be well prepared for the coding questions on Wednesday. Of course, you should also do the other practice problems that I will post as well, but the one that I'll put up after class, probably later today, will be a required one. Today, we are going to finish up linked data structures, and then we'll start on recursion after the exam next week. Did want to mention a couple things that been noticing with the code processor lab, the one that you're currently working on. The first is that, remember, you need to return values from functions that aren't voids. Many of you seem to be forgetting that you need to return values from functions that return, for example, ints. So many of the dummy functions that you didn't have to write, you still had to return -1 from them. And the lab instructions said that, but some of you were forgetting to do it, and grade scripts weren't working for that reason. Others of you are forgetting to return 0 from the write function if the write succeeds. And if you don't return 0, then the CP tester driver function or program will assume that the write failed and will print out a message about how it could not write to the file. Okay? And the C++ compiler apparently is not always warning you about your failure to not return something. So it's substituting an arbitrary integer. That arbitrary integer is not 0. And therefore, the CP tester program says, oh, write failed, and prints out a message. The third thing is that many of you are just assuming if something doesn't work that it's because the output to either standard out or standard error was wrong. It could also be that your output to the file was wrong from the write command. So the description that's printed out by the grade script is a bit long. You have to look at it carefully because it often says, you know, grade script 11 is incorrect. Your file f1.txt is not right. And I've noticed, again, a couple students missing that and just looking at standard error and standard out. Okay, so those are 3 big things I've been noticing. So if you're having those issues, wanted to bring them to your attention. Okay. Also, another issue that's bitten some of you, so just so that you were aware of these things, there is a difference between these 2 statements. Okay, the first one allocates a stack object. And you already have it. After you are done, P is a prize. with some fields in it. The second one allocates a pointer. And that's it. Enough allocates a pointer, room for a pointer. Okay, and it's uninitialized. So for the first one, let's call this P1 and let's call this P2. For the first one, you can immediately start saying P1, say, dot name equals, say, whatever the prize might be, say, a blanket. But the second one, if you try to say P2 name equal blanket, it's not going to work. There's no object there. And if you're lucky, you will segfault right then and there, because P2 will have been set to 0 and you will be trying to access name through an invalid pointer. If you're unlucky, which is what some of you have been, that uninitialized value will point to a valid piece of memory. And it will go ahead and write into that piece of memory and clobber something in your program. Okay? So for example, it might actually write into accidentally P1. And you would see P1 change and you wouldn't even know why. And it might not change P1's name, it might try to write into the points field. Okay, it's just an arbitrary address. So before you can do anything, you have to say P2 equals new prize. To allocate, you need to allocate a heap allocated object and assign its address to P2. So what new does is it creates an object of type prize, taking it off of the heap, and then it returns the address of that new prize object and assigns it to P2. And only then can you go and start to change the fields. If you forget to do that, like I've seen in a couple pieces of code, at some point your program's going to segfault. Okay? And not necessarily immediately. Sometimes after some number of instructions have executed and it's no longer clear what the problem is. So questions about that? Yes, Drew.
Does it make a huge difference if you add the parentheses after the command new prize?
It does.
It would just call the default constructor for it, right?
Yes. So if you leave the parentheses off, that's fine. It will just call it the default constructor.
Okay.
Yep.
Okay.
So that should not be the issue. Other questions? Okay. So here's what we're going to do. You already should have looked at the book and have some idea of how doubly linked lists work. So we are going to go over Sentinel values and circular lists because that is not something the book did. But then I think the best way to kind of work your way in to how doubly linked lists are implemented is we're going to have you work one of the questions from a midterm where you actually are going to do some code reading, because I think that would help you get a feel for how pointers actually work, as opposed to just hearing me talk about how pointers actually work. And the first thing we need to do is actually just finish up with the queues that we were talking about at the end of class. on Tuesday. So remember, a queue is a first in, first out data structure. So inserts occur at the front of the queue. And I'm sorry, we do removals at the front and inserts at the back. So first in, first out, because the first thing into the queue will be the first thing removed. And that's a lot like a grocery line or at a traffic stop, the lines that form at a traffic light. And we went through pop, which removed things from the front of the queue. And then at the end of the lecture, we went through push, which was adding a new item to the end of the queue. So just to review that quickly, we first create a new node. Remember, we will refer to the items of a linked structure as a node. That will be the jargon we use. So we create a new node and assign it a value, which in this case is now. So over here, you see that we've created a new queue node and assigned S to its value field, and we've initialized the pointer to null. And the reason we initialize the pointer to null is because it is the last element in the list. There will be no element after it. So this is our new node, will be the last node in the list. And hence won't point to anything. So that's step one. Okay, we basically allocate a new node and initialize its field. Step two is to link the new node into the list. So step two, link new node into the list. So we make the previous last node in the list point to our new node. So this pointer right here used to be null. So right here, this pointer used to be null. Now we need to make it point to the new node. In order to do that, we cannot just say PTR equals new node. What would happen if we just said PTR equals new node? Why is that not going to be very helpful? Pardon? It would get the value of now. Why would it get the value of now? Okay, but what is PTR? Very good. I mean, here's a PTR, here's a PTR, here's a PTR. What are we referring to? The C++ can't read your mind. It doesn't know what it's like there's 3 Brads in the room, and I go, Brad, well, there's going to be 3 different Brads in this room whose head's going to shoot up, expecting me to talk to them. It's the same thing here. This isn't actually a defined variable. If you try this, you'll get an error message from the compiler saying it's an undefined variable because you haven't told it who owns this pointer. So but there is a way that we can access. So we specifically want to tell C++ that it's the node, this node's pointer. So we do have a pointer to this node. What is the pointer to that node? Last. Very good. So we can say last arrow pointer. And that will set the pointer field of the object pointed to by last to new node. So what this does right here, this is the code right here, it sets the PTR field of the object pointed to by last to new node. So very specifically, it sets this pointer field to be a pointer to new node. And that's what you see right there, is it now has a pointer to new node. Now, there is a special case. The special case occurs if previously the list was empty. If previously the list was empty, there is no last node. There can't be because the list was empty. Therefore, if the list is empty, last will be equal to null. So what this is effectively saying, if the list is empty, okay, then set first equal to new node, because in that case, not only will we end up setting last down here in step 3, we actually finish up by setting last to be equal to new node, because new node is now the last node. But in the special case where the list was previously empty, the new node also becomes the first node in the list. So in the very special case where the list was previously empty, the new node also becomes the first node. Okay? So we have the if-then-else statement there to handle the special case. If it's not empty, then it had at least one node in the list, and therefore last is initialized, and this statement will execute just fine. So questions about this? Okay. So when we go down and we look at the code, now where's the code? Actually, we go up and look at the code. Here's the code for push. So you see that we create a pointer for new node. Then we do our creation and initialization. That was step 1. Here is the code associated with step 2. And here is the code associated with step 3. Okay. Let's say we change this code slightly. Okay? Let's say, because many of you have some problems with pointers, and by the way, if you're struggling with pointers, don't worry about it. It's a hard concept to get, and you will have to struggle with it a bit. Okay? It may reassure you to know that actually, cognitive psychologists have found that when learning is difficult, you actually learn it better than when learning is easy. That may sound counterintuitive, but study after study actually confirms it. The reason, it turns out, is because you work harder at it. Okay? Whereas when it's easy, your brain effectively says, oh, I know it, and it moves on without repeating it. The key to learning, it turns out, is repetition. And when something is hard, your brain has to work at it, and it repeats it multiple times. And the repetition is what fixes it in your brain. When something is easy, you just look at it, you know it, you don't bother to repeat it, and it never gets into your brain. Effectively, it never reaches long-term memory. So while it may be hard, believe me, practice will make this easier, okay? But let's say you're just fed up with pointers and you think, it's so hard, I'm not going to put this asterisk there. I'm just going to allocate a new node off the stack. So now, relieved, you say, oh, I don't need this anymore. And I can just say new node.s equals s, new node.pointer equals pointer, and everything seems to be all nice and good. I don't have to change anything else in the code. And I leave the code, and what do you think happened? So actually, we have our list. So we took away, it was stack allocated. And we'll move up here now. And when we're done, this thing points to here. So what's wrong with that? And last, we made last point to here. So that all worked perfectly. Okay, it's all good. And we've exited. Now, push. What's wrong? Why can't I just do what I wanted to do here, which is just allocate a node from the stack rather than from the heap, and my life's just a lot easier, it seems. Pardon? Very good. So as soon as I leave push, since it was stack allocated, it's automatically reclaimed, which means it goes away. It doesn't exist anymore. And oops, last is now a dangling pointer. We now have two dangling pointers. Right here is one dangling pointer. And here's another dangling pointer. We said what a dangling pointer was last time. What is a dangling pointer? Just a sec, here. Right, points to random memory. Essentially, it's a pointer to an object that has been prematurely deallocated. Okay? Pointer to something that's been prematurely deallocated. So doing a stack allocated object there would fail because as soon as push exited, the new node would be automatically reclaimed and would no longer exist. Its memory is not persistent. We need persistent memory, which we only get when we allocate off of the heap. So that's why we have to allocate off of the heap rather than being able to use stack allocated memory. Okay? Does that make sense? Okay. So moving on. Today we're looking at doubly linked lists, and in Lab 8 you're actually going to do the code for doubly linked lists, so we're not going to be looking at a huge amount of code, although we are going to look at some. And the book actually did a pretty good job of talking about the different operations you need to implement with a doubly linked list. But Dr. Planck has introduced a few wrinkles, so we're going to talk about those wrinkles. So the first thing is that the book did not use a circular list and it did not use a Sentinel node, both of which we are going to use. So we are going to have what is often also called a dummy node. So here I'm going to say dummy node, but it's really a Sentinel node. Okay, so the jargon we use is Sentinel node. Okay, a Sentinel node is a node, so let's define it over here. A Sentinel node is a node at either the beginning or end of the list or end that serves as a marker, as a begin or end of list marker. It is effectively a dummy node. Because it is part of the list, but does not store a value. Or does not hold a value. So it is just there, kind of like a sentinel at a camp, marking the beginning or end of the list. I would write that down. If you have not written that down, you should have. Okay? That's a very important definition. Okay? See a couple people still writing. Okay. Okay, so it's a dummy node, part of the list but not holding a value. So notice that S is the empty string. It's not holding a value. Okay? And it is at the front of the list. It is also, in some sense, at the back of the list. And you might say, wait a minute, I see it at the front of the list. How can it also be at the back of the list? Because it's a circular list. Very good. So if we take a look, first of all, you should know from reading the book today, at doubly linked lists, there are two pointers. A forward link called, I know the book used next and previous, which are more common usage. Dr. Planck uses forward link and backward link, flink and blank. So if we look at the flink pointers, we see that the dummy node or sentinel node points to the real first item of the list, which is give. Then give points to the next element of the list, which is him. Him points to the next element of the list, which is 6. Now 6 is the last element of the list. And when we used a Q, what did the last element of the list point to? Null. Very good. But with a circular list, the last item points back to the first item. And in this case, the first item is our dummy node or our sentinel node. So the last item on the list points back to the sentinel node, and therefore that's why I make the claim that the sentinel node is simultaneously both the first node of the list, but it also stands as a marker for the last node of the list. It's kind of like the head and the tail node at the same time. Very good. And for those of you, by the way, head and tail are also jargon that we kind of never formally define, but we often say that the head of a list is the first element of the list, and that the tail of the list is the last element of the list. Okay, just like a head for an animal is at the front and a tail is at the back. So yes, it's like the sentinel node is simultaneously both the head of the list and the tail of the list. Okay, the same thing is true of our backlinks. So if we just look at the backlinks, the sentinel node, its backlink points to the last node of the list. And then the backlinks continue, and the first item in the list, its backlink points back to the Sentinel node. Thus, again, if we were traversing the list in reverse, we would know when to stop, because when we went from the first node, which is this node, to the Sentinel node, we would know we had reached the end of the list because we'd reached the Sentinel list. So a couple things. For the Sentinel node, its flink points to the first, say, legitimate node of the list. So that is, remember we say the Sentinel node is part of the list, but it's a dummy node. It doesn't actually hold a value. So the first element of the list that holds a value is pointed to by flink. Blink points to the last legitimate node of the list. So we no longer need first and last pointers like we did for Q, because the Sentinel node takes care of those two pointers for us. Okay, so we no longer need to hold either first or last. We still have to store in our list container object a pointer to the Sentinel, and we're going to hold the size of the list. So we still are going to have those two variables that we must store as with a list. And then our list node will contain a value field. In this case, its name is S. And then two pointer fields, one called flink and one called blink. So any questions about this kind of high-level overview of Dr. Planck's doubly linked list? Okay, so it differs from the book in two ways. It's a circular list, and it uses a Sentinel node to denote both the first or the beginning of the list and the end of the list. Okay, so let's take a look now at the API and the implementation. So first of all, we have the dnode object, and as I said, it has a value field, in this case a string S, and pointers to fellow dnodes. Then we have the container object, which is the class dlist. So remember I said that the general idea is that these data structures are container objects. So the list object, in effect, is containing this list of dnodes. Okay, so it's like a container object, and it has its pointer to the Sentinel and the size. And these are protected so that you can't actually get in and modify them. Then the API is fairly straightforward because it's very similar to the API you're given for the doubly linked list STL. So empty returns true if the list is empty, false otherwise. Size returns the size, the number of elements in the list. Push front, what do you think push front does? I'm going to actually start over there. What's push front do you think it does?
Push front?
Mm-hmm.
It sounds to me like it would append it, like put a new node on the end of it.
Okay, so it in fact, now look at push back. So what do you think is the difference between push front and push back?
That's a good point. Probably got
That's
it mixed
okay.
up.
Don't worry. So what do you think push run is?
So we put it on the front of it then.
That's right. So it actually prepends. And push back will append to the back of the list. So push front puts a string at the beginning of the list. Push back will add a string to the end of the list. Okay? Next in line, you in red. What's your name?
Julian.
Julian. What does pop front and pop back do?
Pop front sounded like it would take the first item in the list out of the list. Pop back. Do the same, but back to the list.
Very good. So pop front will remove the first item from the list and return its value. Pop back will remove the last item from the list and return its value. Now, these are used actually right here. These four functions are used for list traversal. Okay, so these two are used for forward traversal. And the back two are used for backward traversal. So begin returns a pointer to the first legitimate. So now I am going to just start saying, I don't want to have to keep saying first legitimate. When I now say first node in the list, I mean the first legitimate node. If I want to refer to the Sentinel node, I will call it the Sentinel node, okay? So when I say the first item in the list, it is the first legitimate item. So a pointer to the first list node. Okay, returns. And RBegin returns a pointer to the last list node. End returns a pointer to the Sentinel node. Not to the last item in the list, but to the Sentinel node. And the same thing for REnd. It returns a pointer to the Sentinel node. Why do you think the two end? If I'm using it for traversal, why should the two end functions return a pointer to the Sentinel node rather than a pointer to the last item of the list? Why is it important that they return a pointer to the last, why is it important that they return a pointer to the Sentinel node? Yes. Pardon? Because what? It wraps around, and the Sentinel node tells you to stop wrapping, right? When you get to the Sentinel node, you know that you are done. Whereas if it returned a pointer to the last node, that's just like any other node. You're not really sure whether you're done or not. The Sentinel node makes it clear that you are done. You should stop. Okay, so before I go on, let's just take a look at those two in action. Okay, so here we are doing our ubiquitous let's reverse a file. And the way we're doing that is we're pushing strings onto the front of the list. Okay, so it is, when we do that, if the file started as give him 6, then the list, if we're pushing things always onto the front, the first item is give, but then we will push him onto the front, and then we will push 6. So we're going to end up reversing things. And then here is our Sentinel node. So when we say D equals L dot begin, initially D points to 6. Okay? Then when we say D equals DF link, D points to him. Then when we say D equals DF link, D points to give. Then when we say D equals DF link, D points to the Sentinel node, and at this point, this condition becomes it becomes false. D is no longer not equal to L dot end. It is, in fact, now equal to the Sentinel node, and we drop out of the loop. So that's how we handle traversing things in the forward direction. Okay? Is that clear enough about traversal? Okay, and the same thing works actually for reverse traversal. Here, we do pushback, and then the items end up in the right order. So when we push things onto the back, the list is give him 6. But we also have reverse pointers. So when we reverse it, when we say D equals L dot R begin returns a pointer now to the last element. And now we say D equals D blink, so we're moving D backwards through the list. And eventually, again, D reaches the Sentinel node, and our end returns the Sentinel node. So again, we eventually will drop out of our loop. Okay. So, continuing back through our API, insert before. What do we think insert before does?
You insert string as before, so before whatever, so like start at this point.
Very good. So we are inserting the string S. So we insert the string S before the node to which n points to. So whatever node n points to, we're going to insert S before that node. And insert after, same thing, except we'll insert the string S after that node. And erase, what do we think erase does?
You erase pointer right from the list.
So you erase that node from the list or delete that node from the list. So that's the API. Okay, so you're going to actually implement this API in Lab 8, and you're going to do some testing with it. Okay, so you're going to need to implement some of these operations, and then actually the book gave you a good practice with inserting. What I want you to do now is look at a problem from one of the midterms. So here is a piece of code that ostensibly is inserting a new node into this doubly linked list, something that you're going to have to write. And there's some code down here you see for doing it. But there's a flaw in the code. So what I want you to do is take about 5 minutes or so and actually try to work out this problem, which is, it says draw the diagram that results when the following code is executed. So this is an exercise in code reading. See if you can draw the diagram that results when that code is executed. And there is a flaw in the code. So in part, the diagram is meant to make it clear what the flaw is. Okay, and feel free to work on this with another person.
Yeah, that's what basic exercise is. What is next? That should be the goal. This will go Overwatch. Yeah, that is correct. Yeah, that is correct.
Okay, I'm tired of waiting to see the 12 o'clock flip over to 12:01. It seems like I've been looking at it for 5 minutes. Shows how time drags when you're just looking. There we go. Okay, so like I said, it's an exercise in code reading. So step one creates a new node, and the name is Brad. And the next and the previous at this point are question marks. And it assigns a pointer to new node. So that's step one. After step one, our diagram looks like that. Step two, it sets new node next equal to current node. Well, current node points to this node right here. So now we're going to make next point to the same node that current node points to. That's what is the effect of setting new node next equal to current node. Okay? If this is a little confusing, let's assign actual addresses. 0x100, 0x200, 0x300. Maybe it'll become clearer. And let's say that 0x400 is assigned to new node, is the address of the object we create. In that case, next right here is going to be 0x300. Previous is going to be what? 0x100. Okay, what's this previous? 200. What is current node equal to? 0x200. Okay, so when we set, and new node will be equal to 0x400. So when we say new node next equals current node, the value of current node is 0x200. So what we're really storing into next is 0x200, okay, which is a pointer to the second node of the list. So then step 3, we set new node previous equal to current node previous. Okay, well, current node is 0x200. It points to this node right here. Okay, and its previous value is 0x100. So what we're assigning to new node previous is the value we're assigning it 0x100. Okay? So effectively, so current node previous is this pointer right here. And when we are done, previous is pointing to that node. So that should be becoming clear that what I'm trying to do is insert Brad before Nancy. So Brad is going in before Nancy and after Ben. Okay, that's the effect of statements 2 and 3. Now, statement 4, so what we're doing is an insert before operation. So this is insert. What we're really doing is insert before. It's as though we have insert before Brad, and the pointer node is 0x200. Okay, so let's look at 4. Step 4 says current node previous equals new node. So that means that current node points here, so we're changing this field right there. Okay, so previous is now, current node previous gets the value of new node. New node is 0x400. So we are making the previous pointer no longer points here. Previous now points back to our new node. Okay, which is right. If we're inserting Brad before Nancy, we want Nancy to point back to Brad. Now our final one is a doozy. Okay, something is going to get the value of new node. So we're trying to make something point to new node. Okay, so current node is 0x200. So we go to the previous, this is 0x200, its previous, its value is 0x400. Okay, so now we go to 0x400, which is new node, and we're setting the next field, this one right here, we're setting that next field to be equal to new node, which is 0x400. Do you all see how I got to the next field for new node? We went through current node. Current node was 0x200. So we first went up to 0x200 and we went to its previous. Previous was 0x400, which took us to this node right here. And now we set its next field, which is right here. We set it equal to new node, which is 0x400. So we made it point back to itself. What were we really trying to do you think, with step 5? What do you think we actually wanted to do if we were trying to insert Brad before Nancy? Yes, Drew?
Have the head next point to the new node.
Well, actually, just instead of telling me head next, what in the diagram, what did I want?
Ben's next.
So Ben's next. Yes. What we were trying to do is make Ben's next. We no longer wanted Ben pointing to Nancy. We wanted Ben's next now to point to Brad. Okay, which is, you can see, current node previous. Well, in the original, the way we originally had it set up, current node previous really did point to Ben. So originally, current node previous really did point to Ben, so then we would be setting Ben's next to the right value. The problem was step 4. Step 4 changed this pointer, made it point to new node. So by the time we got to step 5, current node previous no longer pointed to Ben, it pointed to Brad, and everything was messed up. Okay? So does everyone see that we wanted to make Ben point to Brad? Okay. So step 5 is wrong. The first 3 steps, 2, 3, and 4, those all work properly. But we somehow need to make Ben point to Brad. So now what I want you to do is take a couple minutes to figure out how to fix step 5. And you're allowed to introduce a new variable if you want. If you think introducing a new temporary variable to store something would help, please do so. So take a moment and figure out how you can change step 5 so that we are making Ben's next point to Brad rather than making Brad point to Brad.
You have 2 threes. Why would you do that? It's like this is a spot.
Okay, so here is the easiest solution. The easiest solution, and one that will make someone maintaining your code happy, is define another variable. Call it previous node. And initialize it to current node previous. At the beginning, when the previous field still points back to Ben. Okay, so at that point, it was, remember, 0x100, 0x200, 0x300. So at that point, this was 0x100. So by saving that value, we now have saved Ben. Ben is effectively pointed to by previous node. And now it's very simple. We cross out this and make previous node next. So it's going to be previous node next equals new node. That's the easiest way to fix the problem. Is just to put another variable, a temporary variable in there that holds the value. Yes. So, okay, we'll try flipping lines 4 and 5. I'm just telling you what is the most to someone reading your code. Then we'll flip lines 4 and 5, okay? Before we do that, questions? It does, but it would be, you could also have just said new node previous next equals new node, but that would be incredibly confusing to someone reading your code. Okay, it would work. You're absolutely right, it would work. And looking at the diagram, it was pretty obvious that would work. But for someone who is trying to maintain your code, that's a nightmare. Okay? Pardon? It's just easier having a new variable. So that's kind of, that goes back, a lot of writing code is like writing an English paper. There is ways to write things clearly and ways to obfuscate. So you're absolutely right. Another way that is correct would be to write line 5 as new node previous next equals new node. That would also have worked properly. It's just not as clear, okay? But it would work, okay? Now, let's try the other gentleman's solution. So let's flip lines 4 and 5. Okay, so we're going to execute. So what we have is already, so here's new node. Here's Brad. And we have next and previous. Okay, so we did execute new node next, and it points here. And we have new node previous, and it points to Ben. Now we're going to execute step 5. So first, so we set current node previous, that is Ben. We set its next equal to new node, so that works. And now, in fact, executing step 4, current node previous, we set it equal to Brad, and that works as well. So swapping lines 4 and 5 also work. Okay, I still like my solution better, and the reason is it's very seductive to write it this way rather than line 5 and then 4. Whereas if you store a pointer to previous node, it just is going to reduce the number of bugs. So it's just a good habit when you're dealing with pointers not to try to do. I guess the bottom line is anytime you start seeing multiple levels of pointers like this, it's confusing. And it's easy for it to devolve quickly into bugs that are very hard to find and debug. So try to avoid code that looks like this, okay? And I did that by simply assigning new current node previous to previous node. So I saved Ben in another temporary variable. That makes life a lot easier for someone reading your code like the TA or me. It makes your life simpler. It makes it less likely that you'll have a bug. Okay? So, but all 3 solutions worked. 1, my solution worked. 2, your solution of changing it so that instead of current node here, it was new node. That worked. And the other gentleman's solution of interchanging 4 and 5, so that step 5 was performed before step 4, also worked. Okay? So all 3 would have gotten you full credit, but I really like this solution the best because I think the code's clearest. Okay. Hopefully you maybe thought about copying this code because you might have to use it in one of your labs. Okay. So I'm not going to go through blow by blow Dr. Planck's notes because the book did that and you did some exercises. What I am going to do is point out why he used a Sentinel value or a Sentinel node. Okay? The book, when it did it, let's just look quickly at the book. So let's look at its doubly linked lists and insert. Okay? And if we look at its insert, this is the insert after. We have an insert before or not? No, we only have insert after, it looks like. Okay. So it did insert after. Notice that there are 3 cases. If the list is empty, if we are inserting after the tail, if we are inserting in the middle of the list. So basically, they had 3 cases. Insertion at the beginning, insertion at list end, insertion in the middle. There were 3 cases. Well, 3 cases means 3 opportunities for bugs. We don't like special cases if we can avoid special cases. The Sentinel node avoids special cases. Okay? With a Sentinel node, we never have to worry whether we're inserting at the beginning of the list, the end of the list, or the middle of the list. And the reason is there is always one node in the list. Okay? No matter what, there will be a Sentinel node in the list. So even if the list is empty, there is a Sentinel node. And when we initialize the list in the constructor, so I didn't actually go over it, but there was a constructor, and that constructor needs to make the Sentinel node point to itself. So the forward link points to the Sentinel node and the back link points to the Sentinel node. Okay? So, now we're doing insert. We insert after specifically, where the book had 3 specific cases. Okay? So, if we are going to insert after and we want to insert at the beginning of the list, so we want the new element to be the first element in the list. What should we insert after? The Sentinel node. Very good. So basically, if we want to insert the first element of the list, we simply do insert after, and we would find a way to pass in the Sentinel node. You should be able to figure out how to do that. So you'd pass in the string and the Sentinel node. Okay, there are 2 different functions that return the Sentinel node, so you should be able to figure out how to pass in that to the Sentinel node. Okay, let's say we wanted to insert something at the end of the list. We want to insert after the last item of the list. How do we do that if we have a Sentinel node? Pardon? Put it before the Sentinel node. So how do we put it before the Sentinel node? If we have the Sentinel node, how do we, quote, get the, we're putting it before the Sentinel node. So we have to insert after, we're inserting before the Sentinel node, which means after the last item. And how do we have to have a pointer to the last item? If we have the Sentinel node, how do we get the last item? Pardon? You can't subtract 1. That's not, you can't do that. What? Pardon? B-link. Use the B-link. The Sentinel's B-link points to the last item in the list. So you just write insert after as if you only write one case. The case you write is inserting into the middle of the list. That's the only case you have to write. So the case you write is the one for inserting into the middle of the list. Okay, and because there's always a Sentinel node in the list, as long as you call insert after with the appropriate node, you can make insert after insert into either the front of the list or the back of the list. So the advantage of Sentinel nodes is they get rid of special cases. They actually allow you to write less code in the long run. And when you write less code, you typically have fewer bugs. So Sentinel nodes on Sentinel values are good, and they are something you are going to see again and again in Dr. Plank's notes. I will also, last thing, so two last things. One, there will be a after class exercise, so check piazza.com later today. I will post it. I won't make it due until like Monday, so you have plenty of time. Two, you should check for yourself to make sure that if the list is empty, insert after works properly. It does, but you should convince yourself that if the list is empty and all you have is a Sentinel node, and you try to do insert after, it will still work. And it will, but you should convince yourself of that fact.